So now we discuss the solution of a quiz based on arithmetic instructions of 8086 microprocessor. Here is the question number 1. We need to find the values of AL and CH after the following operations. The operations are SUB, AL, CH and DAS. DAS is basically the decimal adjust after subtraction. The data we need to use for this question is AL equals to 44 and CH equals to 25. So AL can be written as 44, that is 0, 1, 0, 0 and 0, 1, 0, 0. This is 4. This is 4. And for 25, we can write it as 0, 0, 1, 0 and 0, 1, 0, 1. This is 2 and this is 5. So when we subtract, we get the answer that is 1F. If you subtract this AL, this CH from AL, then you'll get this 0001 1111 along with no borrow, no carry. This is 1F. Now as F, any of the nibble is greater than 9, we need to simply subtract 6 from the nibble. So 1 will be same 1 and F is greater than 9, so we subtract 6 from F and the answer will become 9 because F is 15. 15 minus 6, that is 9, so the answer will be 19. So this data will be stored in AL register and there is no carry, so the carry flag will be 0. So the answer is AL, that is equals to 19, and CF, that is carry flag, that is equals to 0. How? Because this AL 44 and CH 25, that represents basically a BCD number. So 44 minus 25, if we subtract, assuming that a decimal number of BCD number, then we'll get 19 as the output. So 19 is the answer we have got in the AL register after the operation. Clear? Next question is AL equals to 25 and CH equals to 44. Now AL equals to 25, that is 0010 and 0101, this is 2, this is 5, and CH, that is 0100, that is 4, and 0100, that is 4. So 44 and 25. Now when we subtract it, we get the carry flag is 1 because the 25 is less and 44 is larger, so we need to have a borrow. So the answer will be 1110 and 0001. It's a binary subtraction, and that is nothing but E1. E is what? E is 14 and 1 is 1. Now we need to check whether any of the nibble, any of the combination of 4 bits is greater than 9, and yes, this E is greater than 9. So when E is greater than 9, we need to subtract E minus 6. So we need to calculate E minus 6, and E is 14 minus 6, so it's 14 minus 6, that will be 8. So the answer is 81, and as we have got a carry, a borrow in the figure, in the expression, so we get the carry flag is set as 1. Now the answer will be 81 and CF equals to 1, but the question is, do we really get 25 minus 44 is 81? How? What should we get? If we subtract 44 from 25, then we should get minus 21, but this minus 21 is the wrong answer. What is the correct answer? The correct answer is that this 25 cannot be subtracted, sorry, this 44 cannot be subtracted from 25. So we need to take a borrow. This one is a borrow, and now we subtract 44 from this 125. So when we subtract 44 with 125, that means we get this 1. Now this 181 having this minus sign, that means a carry flag is set, and 81 is the answer. So the answer is 81 along with a carry flag because a borrow initially is taken, because the number from which we are subtracting is lesser than the number which we are subtracting. Clear? Next question is, we need to find the values of AL, AH and CF after the following operation. First we add and then we calculate the instruction, the values of register after AAA. AAA is what? ASCII adjust after addition. So when SCI is just after addition, so we need to check whether the contents of the registers are lesser or greater than something. So this AL is basically 04. So it's 00000100, and CH, that is 3. So this 00000011. When we add these two values, we get 0000000111, and with no carry. This is nothing but 07. 07 as 707 is less than 9, so we need not to change anything. We need not to change anything. That means the content will be same as 07. AH will be 00, AL will be 07, and CF, as there is no carry, so the answer is AL equals to 07, AH equals to 00, CF equals to 0. Clear? Next is question number 4, in which the data in the AL is 7, the data in AH is 00, and the data in CH, which we want to add from AL, add to AL, is 05. So AL, that is 0000 and 0111, add with 0000, 0101. So what we'll get? We get is 110, 1 plus 1 0 0, 1 carry again, then 1 plus 1 0 plus 1 1, then 1 carry, 1 plus 1 0 plus 1, that is 1. This 1 does not go here, so the auxiliary carry does not set. So the answer will be 0000 1100 along with no carry. And this is basically 0C. C is 1100, that is 12. 8 plus 4, 12. 12 is C, and carry flag is 0. Now this C, 0C is greater than 9, and as 0C is greater than 9, what we do is basically we add a 6 in the data. So 0C and 06 is added, and the result will be 0001 0010. And as a carry, auxiliary carry comes from D3 to D4, we have auxiliary carry set, that is AF equals to 1. Now this AF equals to 1 do what? It do basically, it clears, is basically 1 2, 1 2 is 12, and this carry flag is set because we change the, we clears the value of the upper nibble of the AL. So this 1 will become 0, and because of that a carry flag is set. And this 2, any lower nibble, is same. So this lower nibble will be stored in AL. The upper nibble will be stored through the carry flag in AH register, that makes AH as 01. And as there is a carry, there is a carry, that means CF is equals to 1. Now what is basically carry in this particular case? Now when we add two BCD numbers, or two decimal numbers from 0 to 9, then in this case is 7 plus 5, then what we get is 12. 12, that means actually the result is greater than 9, and when the result is greater than 9, it has to be stored in two different registers. So the one register in which we are using the upper bit, that is 1, is higher register, that is AH, and in the lower register, that is AL, we are storing the lower bit, that is 2. So 1 2 is stored in two different locations, 01 in AH and 02 in AL, and this carry flag in says that there is a carry in the BCD addition problem. So 7 plus 5, that means 12. A carry is generated because the number is greater than 9, so carry flag is set, and the two numbers 1 and 2 are stored in different registers, AL and AH. AL stores the lower nibble, lower bit, lower number, and AH stores the higher number, the upper number. Clear? Next question is, subtract AL comma CH and use ASCII just after subtraction, before after subtraction. So the data is AH equals to 00, AL equals to 04, and CH equals to 03. So when we subtract 04 and 03, what we'll get is 00000001 along with no carry, no borrow, and this is basically 01 with no carry. And as the number is not greater than 9, so we need not to change anything. There is no carry, so there is no need to change anything. AL will be same as 0 1 and AH is same as 0 0. So the answer is simply AL equals to 0 1, AH equals to 0 0, and there is no carry, so CF equals to 0. Clear? Now the next question is very interesting. We are subtracting 0 4 from 0 3. So 0 3 is AL, 0 0 is AH, and 0 4 is CH. Now when we subtract 0 0 0 0 0 0 1 1 and 0 0 0 0 0 1 0 0, that means 3 minus 4. So what we'll get is basically a 1 1 1 1 1 1 1 1. And carry flag is set because we need to take a borrow, because 3 is lesser than the number 4. This number is basically sec 2's complement of minus 1, because 3 minus 4 equals to minus 1. And how we can get the result? It is basically FF. How we can get the result? We actually want minus 1, that means carry flag is 1 and AL has to be equals to 1. So this is done by using the ones and twos complement method. This FF, first we calculate the ones complement, simply inverting the digits 1 by 0 and 0 by 1. So it's every single one will become 0. So the answer will be 0 0 0 0 and 0 0 0 0. It's ones complement of FF. And then we add plus 1, so the result will be 2's complement. And as we know that the result is stored in 2's complement fashion, so the result that is 0 0 0 0 and 0 0 1 1 0 0 0 1, that is basically 0 1, and along with carry or borrow flag is carry flag is 1. So this carry flag is 1 and AL equals to 0 1 is stored in the result. So AL will be 0 1, AH is 0 0, AL is 0 1, AH is 0 0, and carry flag of borrow is 1. Clear? Next question is AL equals to 8, AH equals to 6, and CH equals to 6. And we need to follow the instructions, that is AAD and DIVCH. Now this AAD is basically a sky adjust before division. So before we need to divide the data, we need to adjust in the form of sky digits or BCD digits, so that we can easily divide and store the results in quotient and remainder form in different registers. Here is the example. AL equals to 0 0 0 0 1 0 0 0, that is 8, and AH equals to 0 4, that is 0 0 0 0 0 1 0 0, and that number AX is basically 0 4 0 8. 0 4 is AH, and 0 8 is AL. So the number is 0 4 and 0 8, that is 48 BCD. Now this 48 BCD is represented as this 30. After this AAD command, what this does, it changes the data in AH and AL in this fashion. Why? Because this 48 is basically 32 plus 16. So 32, that means this bit is 32, this bit is 16. So 32 plus 16 is 48, and every single bit is 0. So it will be simply 3 and 0. Now 3 0, and this 3 0 will have 8 as a quotient and 0 0 as a remainder. Why? Because we multiply 8 with uh, 6. Divide. We are dividing. So dividing is basically 48 divided by 6. So when 48 divided by 6, what we get? We get 16. 6 8 ja 48. So it is basically 8. So 8 is the quotient and 0 is the remainder. So 0 is the remainder that is stored in AH, and 8 is this quotient that is stored in AL. Clear? So the answer is 0 8 in AL and 0 in AH. Next question is AL equals to 0 7, AH equals to 0 6, and CH equals to 9. So the result is basically 0 6 0 7, because the number is 0 6 0 7 or 16 in BCD number. So 16 is divided by 9. So what we get when we divide 67 by 9? So we get 9 7 just 63. So 7 is the quotient and 4 will be the remainder. So AL will get the data that is 7 and AH will be the 4. Let's see. AH is 0 0 and AL is 43 because we did the AAD operation. Now why? Because this 67 is basically 64 plus 2 plus 1. This is 64 bit, this is 2 and this is 1. So this will be 67 is basically this is 4 and this is 3. So this will be 43 here. And when we divide the 67 from 9, what we get is basically the quotient. That is, if we divide 67 by 9, so quotient is 7 and the remainder is 4, which will be stored in AL and AH respectively. So AL stored the quotient, AH stored the remainder, and the answer is AL equals to 0.7, AH equals to 0.4. This is quotient, this is remainder. This AL is quotient, this AH is remainder. Clear? Next question is, when we multiply the AL with the contents of BL, and then we use the ASCII adjust after multiplication command. So let's see what is the data. The data is AH equals to 0 and AL equals to 5. So the result is 0.5. When we multiply 0.5 with 0.7, what we get? We get is 35 because it's a BCD data. So 5 multiplied by 7 is 35. So this BL is 7 multiplied. Multiplication gives me the result, that is AH equals to 0 0 and AL equals to 23. Again, why 23 and how 23 is basically this is basically 2. So this 35 equals to 32 plus 2 plus 1. So this 32 bit plus 2 bit plus 1 bit will be 35. So this is 2 and this is 3. So this 23 will be the result after the multiplication operation. Now what this AAM does? AAM stores the remainder in AL and the quotient in AH. Now what the remainder and quotient are? Let's see. This 35, that is 0010 and 0011, it's BCD 35, it's decimal 35, that means 23 hexadecimal. We subtract 10 from the digit and we increase quotient by 1 because we subtracted 1. So this 35 minus 10 will give you 25. 16 plus 8 plus 1, 25. As the number is greater than 10, we need to subtract 10 once again. So another 10 is subtracted and this increases the quotient. So second time we subtract, so the quotient will be 2. And the result 25 minus 10, that is 15. Again it is greater than 10. So again another time we can subtract 10 from the result, and again it increases the quotient. So the quotient will become 3, that is stored in AH, and the result is now 00000101, that is 5. Now this 5 cannot be subtracted from 10 because the number will become negative. So this will be remainder. That remainder will be stored in AL. And quotient is basically the number of times 10 is subtracted from the data is 3. So this 3 will be stored in quotient. So the result will be AL equals to 5 because 5 is remainder. AH equals to 3 because 3 is quotient. And that's the answer. Next question is AL equals to 6 and BL equals to 3. So when we multiply 6 with 3, what we get? The answer should be 18. Let's see. 1 and 8 comes in the AL and AH registers or not. So AH is 0000, AL is 0000 and 0000110, that is 0 and 6. BL, that is 0000 and 0011, that is 3. So when we multiply BL with AL, what we get is AH will be 00 and AL will be 12. Now why 12? Why not 18? Because 18 is 16 plus 2. 16, that means this bit is 1. 2, that means this bit is 1. So the answer, this will be 1 and this will be 2, so this 1 2 will be the answer after the multiply operation. But AAM stores the data in AL and AH as 08 and 01. Why? Again the same operation. 18, if we subtract 10 from 18, then it increases the quotient by 1 and it changes the result of AL by this 18 minus 10, that is 8. Now we cannot subtract 10 from 8 because the number will become negative. So this will be remainder, this will be stored here, and this one time subtraction will change the AH content. So the answer will be AL, that is 08 remainder, and AH, that is 01, that is the quotient. Clear? Thank you.